Good morning. This is Harshul Sagar, entry number 2021 PH10211, and this is my ELL 101 project on diodes as rectifiers. First of all, I shall introduce diodes. Diodes is a two-terminal device which conducts current essentially in one direction. We all know that it has high resistance on one end and low resistance on the other, so it allows only one-way conduction. And this property is what we be using to make a full wave rectifier. And I shall also be demonstrating the full wave rectifier that I have made towards the end of the video. Rectification is perhaps one of the most common applications of the diode. So we know that rectification is a process of converting AC input to a DC input as shown in the figure. We shall further talk about half wave and full wave rectification later. So there could be many possible uses of rectifiers. For example, the main supply for homes needs only a small amount of DC voltage, while the main grid provides only alternating voltage. So there is a need to convert AC to DC, and these are some possible areas where rectification might be handy. So first, let us begin with half-wave rectifier. So if an alternating voltage is applied across a diode in series with the load, a pulsating voltage will appear across the load only during the half cycles of the AC input, during which the diode is forward biased. So let us see what this means. So this is the circuit diagram for the half-wave rectifier circuit, and we'll see that when the current is flowing through the diode such that it is in the path, the diode is forward biased, then the diode will conduct. But if the diode is reverse biased during the negative half of the cycle, then it will not conduct. So therefore, we will get a half rectified output form. So let us further examine this. So for example, here I have shown that in the positive half cycle, we can see in this figure, the diode is forward biased. So the current flows through the diode and the bulb glows. However, can we say the same for the negative half of the cycle? Still, will current flow through the bulb and will it light up? The answer is no. Why? Because here the diode is reverse biased, and we know that when the diode is reverse biased, it does not allow the path of current through it. So therefore, it does not conduct, and therefore the waveform is not completely rectified. Now we come to the center tap full wave rectifier. Before this, let us have a look at the apparatus required for this. We have a center tap transformer, full power sources, capacitor, LED, and diode. So let us see how this basically works. This is the circuit diagram. We can see here in the previous case, we were only having half rectification, but here the full wave is getting rectified. So how is this circuit achieving the full wave rectification? We will try to understand that. So when the point C is at a higher potential than point D, the diode D0 is in forward bias. Here is the diode D0, and the diode D1 is in reverse bias. So the diode D0 conducts and current flows through A to B. So let us see how this is happening. Here we can see the C point is at higher potential than D, and center tap transformer, it is connected to bulb, then to two diodes. So the current will flow through diode D0 and it will be able to conduct, and the bulb will light. Here, if we consider the negative half of the cycle in which D is at a higher potential than C, then the diode D1 this time will conduct and the diode D0 will not conduct. Why? Because D1 here is forward biased and D0 is reverse biased. So again, if we see, this bulb allows only the unidirectional flow of current through it. It lights when the current is flowing through the path A to B. So here the diode D1 conducts, and we notice that the direction of current, whether it was case 1 when C was at higher potential or whether the case 2 where D was at higher potential, the direction of current is from A to B only. So we have achieved full wave rectification. Now we come to the role of the capacitor in this full wave rectification. So actually what will happen over here is that we won't get the exact pure DC voltage, there will be ripples, as you can see in the output waveform. So what we do is that we place a capacitor, and when the voltage across the capacitor is rising, it gets charged, and if there's no external load, it remains charged to the peak voltage, and when there is a load, it gets discharged through the load. So this way we can assure that the ripples are eliminated in our output waveform. Similarly, there is also a bridge full wave rectifier that we can use. So what is the function of the bridge full wave rectifier? Basically, here the diode D0, D2 will conduct in the positive half of the wave cycle, and D1 and D3 will conduct in the negative half of the cycle. And here also the direction of current through the bulb will all be same in both cases. So the output waveform will be fully rectified, as we can see. in the positive half of the wave cycle and in the negative half of the cycle when D is at a high potential. So in both cases, the bulb will glow and full wave rectification will be achieved. We have investigated the role of diodes in rectification. So it was observed how the property of the diode to allow only current in one direction, this can be used to achieve half wave rectification, and then this idea we extended to full wave rectification also. So besides this, diodes can be used in logic gates, in adders, subtractors, clamping circuits, etc. There are numerous applications. These are the references for this project. Thank you. I hope you liked watching this video. So this is the model of the full wave rectifier that I've made using the center type transformer, diode and LED. So when I switch it on, I can see that the LED is glowing. Thank you.